Okay, so let's talk about something you see every single day but probably never think twice about. Why are plants green? I mean, it seems so obvious, right? But what if I told you it's actually one of the biggest, most counterintuitive mysteries in all of biology? Well, today, we're going to dive into some really groundbreaking science that seems to have finally cracked the code.
All right, think about this for a second. We learn in grade school, right? Black absorbs all the colors of light, which means it absorbs the most energy. So if you're evolution and you're designing the perfect solar-powered machine, shouldn't it be black? Why on earth would you make it green, the one color that reflects away the most abundant light the sun has to offer? It just doesn't make sense. It feels like a massive bug in the system.
And this isn't just, a fun little thought experiment. This is a real scientific puzzle, one that actually makes us question everything we thought we knew about how energy and efficiency work in nature.
Yeah, our gut instinct, our common sense, tells us more is always better. More light, more energy, right? So a black leaf, just soaking up every single photon, that should be the evolutionary grand prize. But it turns out nature is playing a completely different game. It's way more clever, way more subtle than that.
And that brings us to the core of the issue. See, the problem isn't really about getting the most raw power. The real trick is managing it.
So here's the key idea, the real shift in thinking. For a tiny living cell, a massive, unpredictable blast of energy can be just as deadly as not having enough. It's not about how much you get, it's about how stably you can use it. You want a smooth, reliable trickle, not a fire hose.
And scientists have a name for this problem. They call it noise. And it makes perfect sense, because sunlight isn't this constant, steady beam. It flickers. It changes every time a cloud passes overhead or as the sun moves across the sky. For the super delicate machinery inside a plant cell, this noisy energy is a nightmare. It's kind of like trying to run your expensive computer on a power supply that's constantly surging and dipping. It's not just inefficient, it can actually cause serious damage.
This image here really drives the point home. Look at that crazy, jagged blue line. That's the input. That's the chaotic, noisy energy coming from the sun. But what the cell actually needs to live is that smooth, steady, dashed line. That's the goal. So the entire job of photosynthesis is to figure out a way to turn that chaotic mess into a clean, quiet, predictable stream of power. So the billion-dollar question is, how did evolution solve this mess? Well, not with brute force. It used something incredibly elegant, a design that's basically like a perfectly, finely tuned antenna.
And you know what's wild? This isn't just a problem for plants. The scientists behind this research point out that this is a universal design challenge. It applies to everything from our own national power grids to the neural networks inside our brains. We're still struggling with it, but it seems like nature figured it out billions of years ago.
Okay, so here it is, the big secret. The solution isn't to put your collectors right at the peak of the sun's energy. No, the trick, the genius of it, is to place them on the steepest slopes of the light spectrum, right where the energy level is changing the fastest. Now, I know that sounds completely backward, but trust me, this is the key to creating that stable, steady power flow.
Let's break down what that actually means. So, what happens if you get it wrong? Well, if you tune your little antennas to absorb colors that are too close together, you get what's called an over-tuned system. It becomes way too sensitive. Every tiny flicker of sunlight, like a cloud passing by, sends the whole system into a panic. The output is just as noisy and chaotic as the input. Total failure.
Okay, so what if you go in the opposite direction? Well, if you set your absorption points too far apart, you get a poorly tuned system. And this creates a whole different kind of problem. The system actually starts generating its own noise, its own internal chaos. It's always lurching between too much power and not enough. It's just inherently unstable and super inefficient.
But then you have the fine-tuned system, the Goldilocks solution, just right. By placing those absorption points on the steep slopes of the spectrum, it creates this perfect, balanced, noise-canceling setup. It literally takes the noisy input from the sun and smooths it out, delivering that clean, optimal power we saw before. And that is why plants are green. They reflect the peak energy in the middle, the green light, to absorb on the slopes.
Okay, so that is a really, really cool theory. It sounds great on paper, but does it hold up in the real world? Does it actually match what we see in nature? Well, this is where things get really exciting. So, the scientists built a model based on this whole noise-canceling idea. And it makes a ridiculously bold prediction. It says, just tell me what the light looks like in any environment, and I'll tell you the exact colors an organism should be absorbing for optimal stability. I mean, that's a bold claim. So let's see if it's right.
First up are familiar green plants, sitting out in the full sun. On the left, that's what biologists have actually measured in the real world. On the right, that's what the model predicted. Look at that. It's almost a perfect match. That's just wild.
Okay, what about a totally different situation? Let's take a look at these purple bacteria. They live under the canopy of a forest where the light is filtered and totally different. Again, left is reality, right is the model's prediction, and wow, it nails it again, a near perfect match. All right, one more, let's really push it. How about green sulfur bacteria living under 2 meters of seawater? The light down there is completely warped. And look at that. Even in this crazy extreme environment, the model gets it right. It's stunning.
So when you average it out across all these completely different organisms living in totally different worlds, the model is 98% accurate. 98%. That's not a coincidence. That's not a lucky guess. We're looking at a fundamental rule for how life harvests energy on our planet.
So what's the big takeaway here? Why does this matter for us, beyond just being a cool science story? Well, because this core idea, this principle of turning noisy, chaotic inputs into clean, stable outputs, it has massive implications for how we design our own technology.
This is more than just a lesson from a leaf. It's practically a blueprint from nature. I mean, just imagine. Solar panels that don't just suck in raw power, but have this built-in passive noise-canceling feature. They'd be more efficient, they'd last longer, especially on cloudy days. Or what about our power grids, or our communication networks? Designing them with this principle could make them so much more stable and robust. Basically, nature has already done billions of years of R&D for us. We just have to pay attention.
So the next time you look at a simple green leaf, I want you to remember it's not some evolutionary mistake. It is an unbelievably sophisticated piece of noise-canceling tech fine-tuned over billions of years. It's a design that completely flips our idea of efficiency on its head. It tells us stability is more important than raw power. And it really makes you wonder, doesn't it? What other elegant genius-level solutions are hiding all around us, just waiting in plain sight for us to finally ask the right question?